So we are starting a new unit, Unit 5, Applications of Differentiation. And this is a pretty short unit. There are really only 3 applications we're going to look at over the next couple days. And we'll do a quiz at the end of the term, but there won't be a test on this unit. The first application is something that you saw before in Algebra 2 and in Pre-Calc, optimization problems, where we want to find a maximum of something or a minimum of something. In Algebra 2 or Pre-Calc, though, you did these by graphing something on the calculator and doing second calc max, second calc min. We're going to see how to do these for real using some calculus. We're going to do one example in our notes so we can write down the process, and then you have a packet of in-class examples, and we're going to start working our way through those for the rest of our notes. For our first problem, so this is section 3.7 in the book. For the first problem, a 3-sided fence is to be built next to a straight section of a river. There's 96 feet of fencing available, and we want to find the maximum enclosed area and the dimensions of that enclosure. Please take a moment and just copy down that problem. To deal with something like this. Step number 1, we need to determine a primary equation, something we want to maximize or minimize. And you know what, before we do that, I think we should draw a picture of what's going on here. Got a straight section of a river. That's my river. There are my 3 sides of the fence. I'm going to put some variables on there, x, y. I know the top's going to be x. Then, like I said before but didn't write down, I need to determine what I call primary equation. Which is what we want to maximize or minimize. Step number 1 in one of these problems is I need to determine what I call the primary equation, what we want to maximize or minimize. Now, we were told to find the maximum enclosed area, so I want to maximize the area. My formula is going to be A equals, okay, well, what's the area of this rectangle? Just x times y. This is my primary equation, the thing I want to find the maximum of. Problem is, I have too many variables here. I need to figure out a way to write this in terms of just one variable. That's going to be my second step. We were given a little bit of additional information. We are going to use that additional information to create what we're going to call secondary equations. Find all secondary equations and those secondary equations that will let us write our primary equation in terms of just one variable. Oops. Step number 2, find all secondary equations, and those secondary equations will let us write our primary equation in terms of just one variable. Get that copy down. So the secondary equation here is they told us 96 feet of fencing available. Well, that sounds like the perimeter to me. My secondary equation is going to be the perimeter of this equals 96. Well, x plus y plus another x gives me 2x plus y equals 96. I'm going to go and solve this thing for y. I'm going to turn this into y equals 96 minus 2x. And the point is, I can then plug this in to my primary equation to get my primary equation just in terms of x. A is going to equal x times 96 minus 2x, or A is going to equal 96x minus 2x squared. And the whole point is I now have a function that I can go through some stuff to find the maximum, or in other cases, the minimum of. Before we go on and actually find the maximum, though, the third thing we're going to have to do, because it's going to help us deal with our maximum, is I need to find the domain of our primary equation. Find the domain of the primary equation. Now, if you look at A equals 96x minus 2x squared, you should realize domain is all real numbers. But that's not actually what I'm talking about here. I want to find the domain of this thing using the physical constraints of like what x and y stand for. Using physical constraints. What I mean by that, oops, let's go in a little more, sorry. Okay, what I mean by that, I know that x has got to be some positive number. Actually, just for our purposes, let's say x is greater than or equal to 0. I know it really shouldn't equal 0, but let's say x is greater than or equal to 0. But there's also a maximum that x can't be over. And I guess the idea is I also need y to be a side that's greater than or equal to 0. If x is like 50, for example, I know this side is 50 and this side is 50, that adds to 100. That's too much because I only have 96 feet of fencing available. This other side would be -4, which doesn't make sense. Can you figure out what's the absolute most that x could be, well, not quite be, but get really close to, so I still have some other side available for y? I think that's just going to be 48. Because the point is, if x is 48 and this is 48, those add to 96. That leaves me with nothing over there. So if you're just a little bit below 48, you'll still have a little bit of a side over there. I now need to go and find the maximum of this thing. Now, do I want to know the absolute maximum or a relative maximum? Do I want the absolute biggest area or just a big area? Well, I think I want the absolute maximum or minimum, which is kind of why I did this domain thing. I want the absolute maximum, or minimum in other cases, and I'm going to try to use the candidates test if I have a closed interval, which again, my domain has now set up for me. There are going to be some times when I can't do that, more with that in a moment. We're going to move on and say step number 4 is find the absolute max or min of the primary equation. Using the candidates test. If we're trying to do this on a closed interval. If we're not on a closed interval, there is another method we'll look at to find an absolute max or min that we're going to call the global justification. We'll see that in a little bit. if we're not on a closed interval? And then when we're done, we'll interpret the answer. Copy this one down, and then we'll actually do this. Okay, so I had my formula A equals 96x minus 2x squared. I want to find the absolute max of this, so I'm going to go use the candidates test. My derivative is 96 minus 4x. Oh, maybe I'll do some factoring with this. I'll take out a 4, and I'll say 24 minus x, which gives me a critical value at x equals 24. If I'm using the candidates test, I now need to set up my little table. X, a of x. I want to use my endpoints. That's why I did that domain. That's why I got 0 and 48 in there. And my critical value of 24. We're going to plug these three values into a of x, our original formula for the area. We're going to get 96 times 0 minus 2 times 0 squared. 96 times 24 minus 2 times 24 squared. Yes, we're going to use a calculator for this. 96 times 48 minus 2 times 48 squared. Go use the calculator and do those calculations. Well, this first one should give us 0, which makes sense. If you have like no length and one side, your error is going to be 0. This is going to be 1,152. This one's also going to be 0, because if we have 48 on one side and 48 on the other, then the other dimension is 0, so our area is 0. I think it's pretty clear where the max is. Our max is right over there. We were asked for the maximum area, so we're going to say our maximum area is 1,152 feet squared. I'll put some units on that. We were also asked for the dimensions that lead to that. Well, my dimensions, let's see. I just need x times y. My dimensions are 24 feet by, well, whatever my y value is. My y value, according to a formula that I had over here, my y is 96 minus 2x. So I'm going to say 96 minus 2 times 24, 96 minus 48, that's 48 feet. Our justification is using the candidates test, maximum area, and those are the dimensions. We're just going to see a whole bunch of other variations of this as we work our way through the packet of in-class examples of optimization problems. And when you go to do the homework, I really think the way you should do it is just try to match up a problem there with a problem in the notes, and kind of use that to guide you along the way. There's not going to be anything in the homework that's too different than what you're seeing in the notes.